6:15. I'm going to go ahead and get us started. Let the online people slowly trickle on. But thank you all for coming tonight to our winter lecture series that has slowly spread and spread from January to why not March? So yeah, snacks, sodas over there. Bathrooms are right outside of those doors if you need it. And then those doors there are not actually emergency alarm doors. So if you need to exit, you can use those doors. They're just a little stubborn. Give them a little shove. Yeah, I'm Ned Bowman, and I am the Outreach and Education Coordinator for the Great Basin Bird Observatory. And we started doing a winter lecture series a few years ago where we highlighted local bird research and bird goings on. And then it slowly spread to encompass other fun things going on at UNR. And so I like to continue that spirit and feature Guillermo here, who's going to talk to us tonight about his research with Western fence lizards. So this is actually the last webinar of our winter lecture series, so you'll have to stay tuned for future ones to be announced. But you can find us at gbbo.org on our website where we post our events, and we're Great Basin Bird Observatory on Instagram and Facebook, where we also post our events. And tonight's webinar will be recorded and published on our YouTube channel, where you can find other presentations that we've done in the past recorded as well. So without further ado, I'm going to turn this over to Guillermo. Let's try it.
Thank you.
All right.
Last slide. I'll just go to. I'll spoiler everybody. This will be. I don't see the mouse. Okay.
You got that, Guillermo?
Yeah. Thank you. All right, cool. Thank you for having me. Thank you for coming. And it is an absolute pleasure to be here to the few people that showed up tonight. Thank you so much for coming. I'm here to talk about objectively the best kind of bird, a lizard, and how they are much cooler and superior than these animals that fly that you guys like so much. I'm kidding, I like birds too. So as Ned said, my name is Guillermo, and I wanted to talk a little bit about myself before I start talking about lizards. So I'm originally from Barcelona in Spain, and since I was very little, I've known that I've liked animals, not specifically birds or, I know, not specifically birds or lizards, but animals in general. And when I was in Barcelona, I started by getting my bachelor's in biology, and then I ended up working for the Spanish government for a bit, studying this fish and how it's not surviving in this marshland ecosystems in the Mediterranean. And things are not going well for it, but it was very cool to understand this. And from there, I moved to Trinidad and Tobago, where I studied this other fish called the guppy fish, which is a very common aquarium fish, and how it evolves rapidly in the streams that flow down the northern range of the island. And although I really like field work in both of these places, I was very curious to understand what was happening in there. So I wanted to get to as deep as I could into it, and that's why I moved to Finland to do my master's thesis in theoretical biology. So not focusing on any one specific kind of animal, but just developing mathematical models to understand how evolution and ecology work. And actually my master's thesis is about the evolution of altruism between siblings, which has important implications as to why does sort of eusociality, through ant communities and termite communities, how they can evolve from scratch, from regular insects. So how can a worker ant sacrifice her entire potential to have offspring to help a queen? So from there, having done a lot of work in the field and having thought a lot about things in a whiteboard in an office in Finland, I decided to sort of find an opportunity that would allow me to integrate this stuff that I've learned from the theoretical perspective with the stuff that I learned in the field. And that's why I ended with a series of crazy consequences right here in Finland. So my plan originally was to study anole lizards, which is this kind of lizard that is very common in the Caribbean. And I did end up studying a little bit of a nose in doing some work in Panama, in the Panama Canal, with this species of lizard, the slender nose. But for a series of continuing the series of crazy circumstances, I ended up studying lizards in the Great Basin Desert right here in Reno, Nevada. And I would say that although this journey has been crazy, it has been amazing. It has allowed me to learn a lot of things. And the thing that I'm truly interested in studying these lizards right here in the Great Basin Desert is about one specific thing that they have to deal with that is very, very prominent in deserts, and that is temperature. So if you think about all of the abiotics, so like non-biological things that might affect an organism, temperature plays like an extremely disproportionate. Like temperature is one of the most, if not the most important abiotic factor that all organisms on Earth have to deal with, right? So here is a map of the annual mean temperature of the world. And from this map alone, we can extrapolate a ton of information as to how many species can we find in a given spot, what is the diversity of species. Because this temperatures change over the year, we can predict where and when are different species going to occur, for example, with migratory birds, et cetera, et cetera. Now, to deal with the fact that temperature is so important in sort of determining where and when do organisms occur, animals in particular have developed two like major strategies in order to deal with the fact that temperature exists. And that is sort of being either in very broad terms, there's a lot of exceptions here, being either an ectotherm or an endotherm. So starting with endotherms like a coyote or the sage grouse, or me with the mountain chickadees. Thank you, Ben, for the photo. The cool thing about this kind of animals is that they have developed a set of adaptations that allow them to produce their own internal body heat. So they have a series of metabolic machines that allow them to generate heat and maintain their own body temperature constant, right? Now that's great because if my body temperature is constant, I can perform at the top that I can, meaning I can survive and reproduce regardless of what temperature the climate is, right? But that comes at a huge metabolic cost. So if I have to keep that machinery running, that means that I have to consume resources constantly. So like that has made endotherms very, very successful and has allowed them to colonize sort of regions of the planet that ectotherms have never been able to. But again, this comes at a huge metabolic expense. Now, on the other hand, we have ectotherms. So that is the vast majority of animals on Earth, both like in terms of species, in terms of volume, in terms of mass, anything that you can think of. And the difference is that ectotherms do not have mechanisms to generate their internal body heat, right? So they, in order to be at a certain temperature, they depend on the temperature of the environment. So they have extreme sensitivity to the temperature conditions that they experience, right?
I need to interrupt you.
Interrupt me, yeah, please.
I have forgotten to share the screen.
Oh.
So our webinar attendees are looking at a lovely image of your face, but they have no idea what you're talking about.
Share the screen.
So I will try to do that if I could find the mouse. I'm sorry, guys, for the interruption here. Oh, and of course I have to enable.
Next question. And I know it's an amphibian from the Great Basin, but now I'm choking. Thank you. I think this is like a frog from the Great Basin. I'm not. Yeah. Okay, so like the thing with ectotherm. So again,
I need to
make sure that there is.
I need to actually share it. I've enabled it to be shared.
That's the one out of 4 birds that there's 3 of the 4 birds that I'm going to show in this time. I'm sorry. Yeah, like there's 2 of the same species. So, all right. Can everybody see me okay online? There's nobody. Okay. So the thing with ectotherms in particular, right, is that they have a disproportionate dependence on the climate that they experience in order to be able to perform, in order to be able to do anything that contributes to their survival and their ultimate reproduction, right? So this is kind of the cycle that I am trying to understand by studying lizards here in the Great Basin. And that is that in ectotherms, the climate, so meaning the temperature, especially, and the precipitation and other factors, have a disproportionate effect on where they occur in space and in time. And I'm talking about from global biogeographical patterns to like very, very small scales to the level of individual territories. And where do they occur in time, both in seasons and like even in daily cycles? And also climate in ectotherms in particular, in endotherms as well, but like in ectotherms, it has a much of a greater impact. Climate also influences their characteristics. So meaning things like their physiology, their reproductive strategies, and even their behavior. And the interesting thing about this is that both their occurrence in space and time and their characteristics mutually influence each other in this sort of like feedback cycle, right? So this is a challenge by itself. So understanding how climate influences occurrence in space and time and characteristics and how these two things influence each other is a big challenge that is still not resolved. The problem is that there's a particular endotherm in this planet that has developed a set of behavioral adaptations that have a disproportionate impact on the climate. And that endotherm is us, right? So we have, because of this set of behavioral adaptations that we have developed industries, etc., which has led and we are going to continue to warm and many other bad things, but we're going to warm the atmosphere and increase the surface temperature across or the entire planet, right? So this is the challenge. We want to understand how, how climate is influencing occurs in space and time and characteristics of species now, such that we can predict how changes in climate might influence both of these things. And with the ultimate goal of like, if we understand this cycle, if we can predict it, we can plan to prevent, for example, extinction of species or implement more effective conservation. Now, the reason, like, in the way the organism, the sort of the species in which we're trying to understand this cycle is, of course, the Western fence lizard, or Sceloporus occidentalis, which is one of the most common lizards in the Western United States. And it's also objectively amazing, as you guys can see from this picture. This is a very lovely male. So the way we're doing is by tracking two populations that occur along an elevation or gradient in the Great Basin. So we're tracking two populations. One of them lives in Virginia Peak, which is at approximately 8,000 feet in elevation. Virginia Peak is located in this range, which is called the Para Range. And it's right by Pyramid Lake. And if you go down this Para Range in the Mullen Pass, which is the sort of the final bit that sort of descends into Pyramid Lake, we are tracking another population in this valley called Mullen Pass that is located approximately at 4,100 feet of elevation. We've been doing this for 2 years. We have tracked over like 500 individuals at this point. But sort of before I share with you the things that we've been able to learn from these lizards, I just wanted to give you guys a tour of what the daily life of these lizards looks like. Let me start with the high elevations. So this is some drone footage that we took ourselves of our high elevation site located in the top of Virginia Peak. And just from these images, we can tell that this is a spot that is comparatively at a much higher elevation than anything surrounding it, right? Now, also from the amount of vegetations, we can tell that it rains much more here, and more importantly, that it is much cooler than anywhere around, right? And as you guys can see in these rocky areas here, you can see if you pay attention, you may be able to see some of us catching lizards in between the rocks, but we often find them like just hopping around the rocks, tracking the areas where the sun is shining and whatnot. And as you guys can see, like the view from up here is absolutely incredible. And I've talked to a lot of people about this place, and it seems to be pretty unknown, which I am very, very happy about. So as I was saying, one of the cool things about this location is that it gets really cold. So this is a photo from this is May 17th, right? So this is last summer, which was exceptionally cold, as many people can tell you. It rained a lot, but still, just so you guys get an idea, the low elevation site was completely out of snow, and there was like accumulations of snow that were taller than me even like at the beginning of the summer. We had snow all the way to June up there. The lizards didn't seem to care. That was one of the cool. This photo is definitely not staged, but the lizards didn't seem to care and just like we're pretty active around the snow. But just so you guys get a couple of pictures of how it looks like, it's amazing. It's out of this world. It's like this massive rocky formations that like grow at this ridge of a hill that like goes down the mountain. And what we usually do is we like walk around this terrain and we try to catch any of the lizards that we see. This is Noah Ratia, who's another graduate student in my lab, and he's trying to like catch a lizard that he sees on that rock. And there's Akila Gopal, who's another grad student in my lab, and Alison Dornick, who's another grad student in my lab. And they're trying to catch a lizard. Now, the question is, how the hell do we catch these lizards? So there's a secret. We get a fishing pole like this one. We make a mini cowboy noose at the top, and we very carefully sort of pass the noose around the lizard's head, and then we pull. Just like if it was a rodeo for very small animals. It is unreasonably effective because the animals, depending on the animal, they don't see it, right? Like you can like literally be slapping them with a little piece of string and they just won't move. And it is tricky, especially when they are in crevices and whatever, but like you get really good at it with time. But of course, in these two pictures, the hunt for the Zard, as we call it, it looks pretty easy, but it can get a little complicated. So for example, this is two pictures of us trying to catch lizards that either were climbing up or down a precipice. So you can see me there on the left trying to catch a lizard that climbed on this outcrop here. And on the right, you can see me and Akila sort of losing faith that we will ever catch that lizard that just ran down that precipice, right? So an easy thing, like a convenient thing of this high elevation site is that it's located right next to this National Weather Service radar station, right? Which is a radar station that essentially like tracks the position of clouds. And that allows us to like be able to access the site really well because they do a really good job of maintaining the road that goes to this radar station. So this gives us a unique opportunity to access an extremely remote location with our car, park the car right there and start flying our drone, for example. Now, I am almost obligated to show a picture of a bird, so here it is. This is a red-tailed hawk, correct? So we saw it one time, it's great. Next. So, and in contrast to the high elevation site, this is the low elevation site. This video, the production value of this video, we hired like John Williams for the soundtrack, but I cannot play it here because of like copyright issues. But as you guys can see, the low elevation site is much drier. Just like from just looking at how at the general aspect of it, it's much drier. There are sparse trees as well, but like not as many. And we often find the lizards again, like sort of crawling around this like sparse rocky formation. So the outcrops are much smaller, and this allows us to like be able to like walk around them much easier. And just so you get an idea of where the site is located and what is the perspective with respect to the high elevation site. So our site would be this rock right here and this rock right here. And this road that crosses the frame is the Pyramid Highway. That sort of essentially like if you continue left here, you'll get into Pyramid Lake in 5 minutes, right? And so you get a scale of the elevation. The low elevation site sits there, and the high elevation site is taller than the tallest point on this picture. So the difference in elevation is very, very, very noticeable. And the difference in climate is massive. Like we're talking 6 degrees difference, like 6 degrees Celsius. God knows how much that is in Fahrenheit. I'm sorry, I'm from Europe. And a radically different sort of like weather. Here are a couple of pictures of us trying to like catching the lizards in the low elevation site. Again, this picture is not quite representative of the environment that we usually see because this last summer was unusually wet, right? So this looks much, much greener than it usually does. And it gives me the creeps because it's usually like a Mad Max kind of landscape, like completely dry. But again, catching the zards can be complicated. Sometimes you can see me there sort of, again, losing faith over a lizard that just crawled into a crevice and that I will never see again. Another cool thing about the low elevation site is the sheer weirdness of the Great Basin and Desert and the sheer weirdness of the state of Nevada itself. So one of the cool things that happened is that one time I was just looking at Google Maps, I was just looking at the site on Google Maps, and I was like, what the hell is that? There was a hole in the mountain. Then we drove over there and we found it. This is an abandoned silver mine from the 1800s. And we got in there. There was nothing inside other than a lot of trash and a lot of like shells from shooters. That's one of the main danger of this low elevation site. There's a lot of people shooting around us all the time. The lizards don't seem to care again, but we do. And sometimes we have to wear like reflective vests so they see us and they don't shoot us. So going back to sort of the natural history of things, which I think is the reason that like the stuff that we all like the most. And the low elevation site, we see lots of different kinds of fauna. And like just to like show a bunch of like representative species, we see some rattlesnakes. This is a guy that I almost stepped on. This guy right here. It was really scary, but nothing happened luckily. But we often see a lot of mule deer just like running around. You can see them with this like big ears that they have to dissipate heat. And we also see some pronghorn sometimes, but it was too fast. I just couldn't get it. I'm sorry. But the cool stuff about the low elevation site, in my humble and completely objective opinion, is the lizards that we can find over there. So I just wanted to show you a couple of the examples of representative species that we see on top of the western fence lizard. And the first one is the desert horned lizard, Phrynosoma platyrrhinus. And this is an amazing lizard. This is absolutely beautiful. I don't know if you guys have caught one of these guys. They usually call them horny toads because they do look like a toad, not related whatsoever. And this is two guys that were just hanging around in low elevation site. Both of them were males, which is we had this whole theory that either they were lovers or they were father and son. And when we caught them, they seemed to be like pretty close, and then they stayed together. And again, these like animals are so beautiful. Like one of the cool things about them is that they spit blood out of their eyes. I haven't seen it, but I always keep the lizard pointing away from me just in case. And like another cool thing about this lizard is that like if you guys see like the sides of the belly, they have like serrated things, like kind of they have like pointed serrated things. And this is to, if they get caught by a predator, by like a bird or something, they just puff up and then they sort of hurt the throat of the animal that's trying to like swallow, right? The coolest thing about these lizards though is the babies. They are stupidly cute. They are really, really small. This is the juveniles of all of the species that I'm going to show start showing up at the end of August and September. So like if you want to go see babies, like September 5th is the best date of the year. Depends on the weather conditions, but I would say September 5th is optimal. So another of the stars of the show in our low elevation site is the Great Basin color. And this one is also like, it's magnificent. The coloration is fantastic, but they bite really, really hard. Like when we handle them with like kitchen knives, you know, the kind of knife that kitchen gloves, the kind of gloves that you use to like not cut your fingers, because one of the best strategies to like handle these lizards is let it bite you, right? And then you start measuring whatever you need to measure, right? So both of these guys are males, and the guy on the left is one of our favorites. We call him Busted. He lost his tail at some point in his life, and because these lizards are not as good at regenerating their tails as other species, this guy got like some sort of like deformity, and then the tail ended up growing wrong. That does not seem to have any effect on its survival, as we've seen him for 2 years, and he's just running around happily. He controls a pretty big territory, and like there's no other males around it. So, and again, I wouldn't make it justice if I didn't show another picture of a baby. This was taken by my partner Jen over there, and they're like stupidly cute. They try to bite you, they just can't. Yeah. But the start of the show of all of this story is perhaps the most boring lizard in this environment, which is the western fence lizard, and it's also called the blue belly. Like, I guarantee you that everybody in this room, if you've seen a lizard around Reno, it's one of these guys. It is incredibly abundant, extremely easy to catch, which makes it a perfect study organism, because you can catch hundreds of them and you can measure traits on them, like on hundreds of different kinds of individuals. Now, one of the reasons why this lizard is called a blue belly, for essentially obvious reasons, right? So once you flop it upside down, you see that they have blue coloration. And one of the cool findings, like one of those weird ideas that we had at first is like, why are they blue, right? What is the advantage of being blue? And like, what is happening over there? So we had one undergrad in my lab, one undergraduate student who started looking into it. And actually she found out that only the males are blue. the females are significantly greenish, right? And it seems like the blue coloration is associated with the ability of a male to like dominate a territory. Like a more territorial male would be bluer, right? Still have to do a little bit of digging. Now, one of the interesting things you'll notice on this photo is the incredible side coloration of both of these individuals. This individual was 100% posing. This guy wanted to be photographed. This photo was taken at this distance with my own phone, right? So this guy really just like wanted to show himself, right? So this coloration on the side, of course, it's not natural. We paint it ourselves. So we use acrylic markers to paint a unique color code combination. And we do that to identify the individual, right? We actually track unique individuals in both of these populations, and we've been doing so for 2 years. And the way we track them is through a triple approach. The first approach is identifying if it's a male or a female. Now, in this species, it's disgustingly easy. If it has a single postanal scale, it's a female. If it has two, it's a male. And that is to protect their hemipenis. So like the penis is divided in two, right? That's the first layer. So like we know that now that if an individual is a male or if it's a female. The next layer is by toe clipping. So imagine if we see a lizard from the belly, right? And what we do is that we cut one finger from each of these limbs in a unique combination that is sort of specific to a given individual, right? We can use the same code for males or females because essentially we can distinguish it's a male with a unique code, it's a female with the same unique, right? So for example, to identify an individual, we might cut the second finger from one limb, the third from the second limb, the first from the third limb, and the first for the fourth limb, and that individual will be 2, 3, 1, 1. And then when we catch it, we are able to read the code and sort of match that sex and that toe clip code to a given individual, right? I know. It doesn't hurt them, I promise. There's been studies that have shown that even if with like 3 fingers cut in one hand, they still have traction and they don't move significantly slower than lizards that have not had their fingers cut. Another reason why we're very careful when we perform these cuts. We don't cut like the whole finger. We just can't cut a little tip. That has led to some problems, but that has some, like, there's been some issues, of course, with identification, but it generally doesn't cause any problems. And actually, some individuals do not have like some lizards do not have like nervous terminations and at the end of the fingers, so it doesn't, right? So this is cool and all, but like in order to identify an individual using this system, we would need to catch it. So, and sometimes we're interested in like just seeing its behavior without having the need to catch it, which is why we have also marked them with a unique combination of 3 colors that we paint on their sides such that we can see them from a distance. We use there's 7 different colors, and sort of it's the same combination on its sides such that it doesn't matter from what angle we're seeing it, right? So these are 2 examples of 2 of my favorite lizards. On the left-hand side, this individual, actually, you can see a little bit the toe clips, but this individual is color-coded as yellow, blue, green, white baby. And toe clips, actually, you can see this finger right here is cut, this finger right here is cut, this finger right here is cut. I've caught 697 lizards to date. So I can tell you what is the toe clip on this individual without having to like catch it. But for safety, if it didn't have colors, we would catch it. And then the other guy on the left is BVP 5311, which is a female from the high elevation side. And this was H036. This is the biggest lizard we have ever caught. And this is, to my knowledge, the biggest western fence lizard that I have ever seen recorded ever. This individual had like the snout to vent length, which is like one of the key measures that like we use to quantify lizards, was over 100. And that is like comparable to like other species that are much bigger than this species. We also applied the same procedure. We've been starting to apply the same procedure to the colored lizards. And these are 2 individuals, LC036 and LC025 from the low elevation side. And this is a good example to like show the difference in sex between these 2 species. The males on the left-hand side over there have like a much brighter orange coloration, and that allows us to like tell them apart just from seeing tell apart the sex just from a distance. Also, when you catch them, they do have the 2 postanal scales, but it's a little bit trickier to point out, especially with juveniles. So what do we do with this marking system? So what we do is we do this ecological experiment that is called capture, mark, and recapture. And this is perhaps the most powerful ecological experiment that one can design. And it is as simple as we catch a lizard for the first time, call it lizard one. Then we go to the field and we see it in a given week. We don't see it again. We see it again. We don't see it again. We see it again. Now, every time that we catch it, we not only record if it survives or not, we record also where it is, when do we found it, and how big it was, and what kind of behavior was it displaying, and what was it doing, right? Now, for one given lizard measurement, that wouldn't be a lot of information, but if you pile them over time, you can estimate a ton of things, right? So this is how it looks for the two example lizards, but this is our actual data from this past summer, right? So each of these boxes represents like a capture event across all of the weeks that we went to the field in the low and the high elevation sites. And this diagram already gives us a ton of information, right? Like we start going to the field very early, and then at first we catch a lot of lizards, then we sort of plateau, like we only recapture individuals that we have seen before. And then at the low elevation site, we started seeing a lot of new individuals again. And you'll see why in just a second. But at the high elevation site, we sort of plateaued. This summer, we did not see a lot of juveniles, we just saw adults. And we're very intrigued to see what happens next, right? So with this capture, mark, and recapture system, we can also, like, as I was saying, like we can tell a lot of this, of the demographic structure of this population, right? So here I'm plotting the snout to bend length, which is this metric that I was talking about, which is the distance between the cloaca to the snout. And this is kind of like the most used size metric in lizards, because if you measure them from the tail, then they lose the tail. And then you see an animal that shrunk half of its size from one day to another, right? And this is like plotted them over time. No? And on the top row, we have the high elevation side. On the low, we have the low elevation side. And on the left, we have 2022. And then on the right, 2023, the 2 years when we've been running this experiment. And the lines over here sort of connect different measurements for the same individual over time, right? So not only with this plot, we see sort of how the size structure of the population changes over time, but we can see how unique individuals grew over the course of a season, right? For example, on the bottom left at the low elevation side, this gives us a lot of information, right? So like we start the summer in May, then we go there and we see the animals divided into two size classes. So like individuals that are around 80 and individuals that are around 60, right? Now we keep recapturing these animals and we see how they grow to adulthood, and at the end of the summer, we start seeing juveniles. So then that allows us to inform sort of the life cycle of these animals. And if we catch one of those juveniles, we can track it over multiple years. The oldest lizard that we have so far is 3 years old. So an animal that was caught in 2021 by somebody who's not now in the project, but like if she happened to mark it in a way that we could identify it so we can track this individual. And it's likely that it might survive to the next year. It's an individual in the high elevation. Other than just understanding how they grow, we can also understand when, where, and when do they occur in space and time. So this is a map of all of the observations of lizards that we've had in these 2 years. And this, I'm going to show it this way because I had some technical difficulties with plotting this map. But essentially, each dot corresponds to a particular lizard observation, right? So, and as you guys can see, on the second year, we expanded to a different area. We got a ton more individuals. And on the left-hand side, that's something really cool. That's something that like we've been looking into. And this is sort of the distribution of the number of observations that we saw at each hour of the day, right? So if you look at this, it's very cool because the weather changes in the weather conditions over different years led to the lizards peaking in activity at different times of the day, right? The high elevation site, this year, it happened to like peak earlier in activity than the low elevation site, but last year it was the reverse pattern, which is something that we're still trying to figure out how climate led to this pattern, right? Now, because we have information at the individual level, we can sort of map how these observations like correlate to one individual. And this allows us to sort of draw and like get a sense of even individual lizards' territories, right? So we can gather a lot of information of where does a lizard live. And to illustrate this, I'm going to show you guys my favorite lizard that lives right there on that circle. My favorite lizard is L039 Scooby. He's my favorite child. I'm like 100% happy to admit it. And Scooby lives in this sort of area on the low elevation side, and specifically on that rock. We actually took a thermal image, like a flight just over the rock where Scooby lives because he's so important to us, right? And the cool thing about Scooby is that when you go to this rock, I'm just gonna show. Like when you go to this rock, this is all of the times in all of the spots where we have seen Scooby. And actually, we have captured Scooby 19 times. So it's almost guaranteed. Every time we go there, we see it. And he's always doing the same stuff, right? Now, there's a couple of juveniles that popped up around the same area. And there's one juvenile that we call Scooby Jr. because he has the same attitude. We actually call him Scooby because when I tried to catch him for the second or third time, he was in this rock right here. And then I approached it. I know that he saw me. Then I came to it and he started running around the rock. Then I started chasing him. And then the grad student in my lab, Akila, was like, that looks like Scooby-Doo. So then that's how the name Scooby came up. So what do we do with all of this information? So with all of this mark and recapture information, we have a really good idea of where do the lizards occur in space and time within their individual territories and along different times of the day, right? But the rest of the research program that we do in my lab is to understand how the climate is influencing that and how the climate is influencing their characteristics. And the first challenge here is to quantify the climate at a scale that is relevant to the lizard. And this is work that has been led by a postdoc in my lab called Karla Lujeric, she's from Croatia, and a grad student in my lab called Noah Ratia, who's from Sweden. And so you guys can see, lizards love them. This was not staged whatsoever. They have a lizard there on the shoulder and on their hat. This is YSY. YSY is an absolute poser. He is. But anyway, so to quantify the climate at a scale that is relevant to the lizard, we do two things. And the first thing is building operative temperature models, right? So what we do is we scan a lizard with our phones, and then we send that file to a 3D printer in order to print a model of the lizard of the same size. And actually, we have shown that these models printed out of very cheap plastic, like this costs 13 cents to print, have the same thermal properties as the lizards, right? So what we do, and you can see it in this guy, we drill a hole in the middle with a little cap, and then we put a temperature logger inside of this operative temperature model. The risk with that is that birds like them a lot, so we lose them sometimes. But in general, they stick really well to the substrate by just like putting some sticky, right? There's another one. Both of these are from the low elevation side, but we put them in all sorts of microhabitats, even underneath crevices. There's a couple of them recording right now. Now, the temperature loggers inside of this operative temperature models are recording once an hour for the entire sample, and that allows us to have like a very complete temporal picture of all the temperatures that the lizards have available at any point in time. For example, this is all the temperatures recorded, but all the operative temperature models we had deployed on June 10th in 2020. This is just one example, but we have every summer we record more than 500,000 observations, like temperature measurements across all of these OTMs. The other part of our work in quantifying sort of the climate at the lizard level is by doing some aerial thermal photogrammetry, which is essentially saying that we fly drones. We fly thermal imaging drones above the site, and this allows us to capture an amount of information at a level, an absolutely unprecedented level of detail. For example, this is our high elevation site as seen at approximately 8 a.m. in the morning on a Monday, or like on a day in June, right? I can tell you that this is 8 a.m. in the morning because I know the north is pointing here, right? So then the sun is coming up from the east. And as you can see, just by the position of the sun, we can tell that what area of the site is going to be much warmer and what area of the site is going to be much cooler, right? So there's rocks here that sort of prevent the sun from hitting it, and that these rocks won't be able to like heat themselves up until the sun reaches the zenith, or when it goes down, like on the western, like on the sort of, it sets on the west, right? In general, this allows the western side of any outcrop to be warmer in general here in the northern hemisphere, but we are seeing that actually lizards prefer much more the eastern sides of the outcrop, which we are very confused about. The other cool thing that this map allows us to tell is that, like, okay, what is the ability of trees, for example, to buffer the thermal conditions that the lizards experience? So, for example, if we have information in a given lizard's territory, even if that environment is really hot, that tree might be cold enough to like keep it cool at like the peak hours of hot in the day, right? And the principle here is simple. We fly the drone over and over the same area until we have snapshots that are like spatially complete but temporally discrete of the same area at different moments in time. And what we've been able to do, and this is something that we're trying to publish right now, is combine the information that we get from the operative temperature models with information that we get from several flights in order to predict the thermal landscape at any point in time. In the prediction now, you guys are going to see how the sun rises from the east and sort of arrives to the zenith. So like it sort of warms up the space evenly, and then how it sets again on the other side, like on the western side of this outcrop that we were studying. Now this is really cool because this is completely predicted. And if you go there and you actually measure the temperature on the ground, our predictive method is really good so far. But this is amazing. Like I plot these things and I stare at them for hours and I just try to imagine like how do the lizards deal with this. And it's really cool because we have like sort of complete information on all of the temperatures that the lizards will experience over an entire summer, right? As long as we have operative temperature models on the ground, we can tell what temperatures will the lizards experience. How am I doing on time?
Well, you're good.
Yeah.
Maybe 15 minutes.
All right, good. Okay, so going back to this, like now I've talked a little bit of how we're dealing with quantifying the climate. And then one of the other things that we're looking into is, again, the characteristics. One of the key things that we're looking characteristics-wise is in this thing called the pace of life syndrome hypothesis, right? So this is work that is being led by Akila Gopal, who's like a PhD student in my lab. And you can see me and Akila here holding lizard, like the 100th lizard from the high elevation side. And since then, we have this tradition that every time we catch a lizard, there's like 100, 200, 300. We hold it as if it was a marlin. And sometimes we force the perspective to make it look cooler. And we have a whole collection of different lizards, sometimes like with dramatic poses and whatnot. So the idea of the pace of life syndrome hypothesis is that, you know, we see these animals with very complex phenotypes. They have a very complex set of characteristics. And a way to like explain how these characteristics might arise together is by saying that like different kinds of traits covary along predictable axes, right? So in general, like in the broadest terms that I can think of, the pace of life syndrome hypothesis says that things like metabolism, behavior, and thermal physiology might be correlated. So if we see an individual that is very bold, it is likely that it is hypothesized that that individual also has a fast metabolism and has a hot thermal physiology, right? Now, support for this hypothesis is mixed, but we have the perfect system to test it. So one of the things that we do, for example, is measure the temperature of the lizards in the field as an indicator of their thermal physiology, right? And you can see me here taking a thermal image of a lizard that we saw in the field with Akila being almost ready to catch it. And this is how the thermal image looks like. We have hundreds of those. We have a poor undergraduate student that has to just go through another patient, measure the temperature. But usually what we do is we try to aim for the eye, which has been shown to be like the best representative of the internal body temperature of the animal. And if we cannot hit the eye because of whatever reason, we also have the alternative of just like sticking a thermocouple probe up their butt, and that is quite literally to get a representation of their internal body. So this sort of comes from the thermal physiology perspective. But the other thing that we do is that we measure their behavior. And one of the cool things that we study from these lizards is their displaying probability. So sometimes when we see a lizard in the field, this is a very common behavior for all of these lizards. Like one-eyed lizards, they'll start like pushing up at you. They look at you and they start doing push-ups to show you their bellies. I don't really understand why. It is not scary. It's just fun, right? They start like sort of pushing at you. And the thing is that different individuals, and sort of if we take this as an indicator of their personality, different individuals will be more prone to push up at you, to display at you than others, right? They also do head bobs, although they do that much less frequently. Usually it's just like they start pushing up. So for example, this individual right there, the poser, was trying to like push up at me when I was taking the picture, but this guy was just like trying to sneak in, not being sort of detected, no? And that sort of goes from the spectrum. We use this as a spectrum from like, are they generally shy or are they generally bold, right? And one of the things that we found pretty obviously is that size, snout to bend length, is correlated with boldness. So bolder individuals are also bigger. That is sort of to be expected. But what we are truly interested in is how these traits are covariant together, right? So on the x-axis here, I'm plotting the average body temperature of an individual across multiple measurements. And on the y-axis, I'm plotting the average display probability. So if we count displays as a 1 and not displayed as a 0, what is the average probability that we see it displayed, right? Now, if the Pohl's hypothesis, the base of life syndrome hypothesis was true, we should see organisms vary along this axis, where we have bold and hot individuals on one side and shy and cold individuals on that side. Now, we're still trying to figure this out. We have no idea what's happening. It looks like there's other factors at play, and that this hypothesis holds a little bit in the low elevation side, but not whatsoever in the low elevations and the high elevations. We separate this by sexes. We do see that males tend to be hotter and bolder, but it's a very weak correlation. So still a lot of digging to be done in this. Other than just like looking at correlations between traits, we are also looking at the reproduction of these animals. And this is actually my area of research here. So the thing that I'm looking into is about the cold climate hypothesis for the evolution of viviparity in squamate reptiles. Now, so viviparity, and I'm talking about giving live birth, is something that we typically associate with mammals, but it has evolved independently hundreds of times across the animal kingdom, with more than 100 independent evolutionary origins across different squamate species alone. For example, this is an example of a viviparous lizard that is very closely associated with or babies here, the western fence lizards. There's this yarrow spiny lizard that lives in the Sky Islands of Arizona. And these guys that live at very high elevation are viviparous. And this is the first clue, right? So like people are trying to figure out, okay, why are these animals viviparous? The main idea here is that so viviparity evolves as a way to deal with this cold climate, right? So like, and that's why viviparous species tend to be associated with either cold climate at high latitudes, so like farther away from the poles, or at high elevations, especially at high elevations, right? So the idea is that if I'm carrying my eggs and I don't lay them, I can control the temperature at which the eggs grow. And if I can control the temperature at which the eggs grow, I sort of guarantee that they have a higher survival chance. Now, if I live in a very hot environment, I can just lay my eggs on the ground because it's hot. I know that the embryos will develop at more or less of a good temperature, right? So that's the main idea. And that's what we're trying to test with these two populations, right? So this is some of my focus is on female lizards that live in these two populations. One of my favorite ones is L032 Barbie, and we call it Barbie. This is PPP, triple pink. And other lizards at the high elevation side, like that guy, that I'll talk more about in a second. Now, my hypothesis is that if they are at cold elevation, right, they should be closer to being viviparous, meaning that they should lay eggs later in development. And if they are at low elevation, they should lay eggs earlier in development, if this hypothesis is true. Now, here's the challenge. How can you tell if a lizard is carrying eggs or not? Using a handheld veterinary organism, right? So this is something that I am trying for the second time ever, and like at this scale, only because this device was invented in 2015, right? So I can bring this device. This is not exactly the same one, but it's practically the same one. I can bring it with me to the field, charge, and it connects to my phone. And as I'm in the field, you can see me over there. I'm holding a lizard in my hand. I'm scanning it with my ultrasound and seeing if it has eggs or not. Then I record a video, I get it back to the lab, and then I go painstakingly through all the videos that I have. And this is how the videos look, more or less, right? So what we're seeing is a cross-section of a lizard, right? So like this is the line of like the spot where I'm looking at, and we're seeing it upside down. So this is the spinal cord, and that will be the belly of the dog. Just so you guys have a reference, this is 1.8 centimeters, which is this much. So In this picture already, like my eye is very much trained for this, so I can tell things apart much easier because I've looked at a ton of things. I actually been talking with a veterinarian for like a year now. And this is an egg, there's another egg here, there's another egg here, and I can tell you that another one is gonna pop up. So the beauty of this method is that since we're doing mark and recapture, we can see the same animal and scan it with the ultrasound multiple times. This is May 30th. This is June 6th. As you guys can see, the eggs are slightly bigger. I mean, I can tell it apart easier. Then we get into like June 14th, and we start seeing like very much more clear structure. There's one here, there's another one over there, there's another one here, the edge of another one popping here. I have a video, I can tell them. And one of the cool things that we see is that as development grows, so the egg becomes less opaque, right? So like it starts with like a very, like if you see that one, it starts with like being very uniform white color, and that indicates that it's a lot of solid mass, right? And that solid mass sort of starts differentiating itself to the edges in such that we end up seeing the actual embryos, which we cannot tell them apart really well, but they're like right? And then this gets to like a very exaggerated point where like we see the lizard, as you guys can see, we see the eggs physically on the sides of the animal. Like there's no question that this animal is pregnant. At this point, we can even tell apart the shell of the embryo, like of the shell of the egg. And then we do this progressively over time until there's one day when we don't see eggs anymore, right? And then, for example, this individual, last time we saw it with eggs, it was on June 23rd, and then we know that it lays eggs sometime between June 23rd and July 3rd, right? And with this, we're trying to assess the length of the gestation period and see if it's different across populations and across even different individuals within one population. We're still working on that. There's 494 videos to go. So just to wrap up a little bit of everything that I talked about, and going back to this like sort of cycle between climate, occurrence, space and times, and characteristics, we're studying the climate, we're trying to understand the climate via the operative temperature models and the flying images. We have information on their occurrence in space and time via this mark and recapture procedure, and we're trying to understand their characteristics via their studying their physiology, their reproduction, their behavior, etc. And our goal is that this, like collecting this many kinds of different data is very, very complicated. And of course, like the stories that this is telling us are very, very complicated because there's a lot of interactive traits, right? And a problem with biology is usually that we simplify things instead of embracing complexity. So one of the things that we're trying to do is embrace the complexity inherent of the system such that we can make the most sort of comprehensive prediction about how this lizards, and by extension, other lizards might respond to climate change. And before I finish, I want to take a couple of minutes to like thank people and things. The first thing that I want to thank, is the Northern Paiute tribe for like essentially thanking them for allowing us to work in their native lands. We technically, our sites are located in Bureau of Land Management lands, but they are historically part of the Northern Paiute tribe. And it is honestly a blessing for me to like have come from the other side of the world and have found this incredible Great Basin ecosystem. Every time that I'm out there, I just have new ideas and I see things and I get like fascinated. Like my girlfriend can tell you that like I drive around and I get distracted by different outcrops and how they look and how they might be for lizards. And like I judge outcrops based on their sexiness. It's a whole thing. And again, like these landscapes are amazing, and like being able to have your office out there and like just have lunch under one of these trees is absolutely incredible. And I also want to take a second to like thank all of the people that made this possible, and that is everybody in my lab, graduate students, undergraduate students, my advisor Mike, who's that guy right next to the lizard, and my girlfriend Jennifer, and of course the lizards themselves for their amazing, for the fact that they exist in this planet and they let us study them and annoy them as much as we do. And with that, thank you so much for listening. Thank you. Questions? Why not? Why didn't you show more birds?
Can you name another bird species you've seen?
A penguin. No, I said I got stuck at bird species. I've seen crows. Crows, I've seen a ton of them. No, I do see, what are the ones that have a quail? California, those are like really dumb looking. They just like, they have a tendency to like be on to like run in front of cars the moment you get close to them. And I mean, there's a saying, but yeah. I don't remember more birds that I've seen. Oh,
I have a question.
tell me.
So, what is the, percent of the lizards across the landscape that you think that you're actually marking? So of the residents, and how much movement do you see up and down elevations, if any? Between,
Mhm.
so, and who is moving? Are any of these animals like making any sort of like longer term dispersals, or are some of these animals specific to an elevational site? And does that lead to possible opportunities of local adaptation to altitude?
So dispersal between sites, like if we see a lizard that has moved between the two sites that are located like 15 miles apart, like we just like retire it, bring it home, and give it crickets every day. So like in terms of like dispersal within the site, there seems to be like an extremely high site fidelity, which is one of the coolest things about this system. Like that lizard Scooby that I showed is an extreme example, but in general, a lizard, like like if you plot all of the observations of a lizard and you get the center of its territory, the maximum distance between the center of the territory is going to be maybe like 20 to 30 meters, right? So like you have them really, really focus. Sometimes with these, we see movements of lizards between different rocks, but that happens when, like, for example, one adult individual dies, then another individual sort of colonizes that rock. It is possible that we're not catching everything, but in any model that we do, we account for the fact that it's not a closed population. Yeah. And I don't know. I am very curious to see like if there's dispersal across different outcrops, and that's why like tracking this juveniles is going to be really helpful, especially at the low elevation site where it's not a continuous population. So like there's like a road in between. So it's possible that this summer maybe we see some like migration between different rocks. Yeah.
So I noticed when you were looking through your thermal imaging that it certainly seemed at least that
I'll put it again.
that the different paints were actually showing up.
The eye picture here?
That one.
Oh, yeah. Good question. Good question. I know what you
And
mean.
so are you able to use that in any, I mean,
Like
are you able to use the fact that some of those paints will show up on the thermal imaging in a way to help you track them for other applications?
to like track them, I don't know. I wish I could, right? But we haven't looked too much into which colors specifically show up. I'm guessing it's like blue and silver and whatever. But we have actually like one of the things that we are really interested in is the change in coloration even within a single day, right? When we go there really early in the morning, we see them like really dark color in order to observe the maximum amount of heat that they can. And then later in the day, they become really light, right? So one of the things that we're trying to understand is like, okay, what is the range of different colors that they can assume? And at what time of the day is best to achieve each color, right? So like if the whole aim of the game is that they are moving, they're changing colors, and they're doing everything they can to stay always at the same temperature. That's called behavioral thermoregulation, right? So how does color play into this, right? And I had this idea not so long ago, actually, to like, okay, what if we go out there, we take this operative temperature models, and we paint them anywhere from black to white, right? And then we see, okay, like in the same habitat, what is the difference that the temperature measurement records depending on the color of the animal, right? And then can we build a model from that based on like, okay, like this time of the day, the best option for you would be to be this color, but later in the day, the best option for you would be not only to be in this kind of habitat, but also have this color. So that's something we're looking at. Thank you so much. That's such a good question. You go next, man.
I think I wanted to get back on that question too, because in your maps of where they live and where they move, there's a gap.
Yes, that is one thing that happened in the low elevation population, which is this one. So this is like, let me see. So this is what happens, right? So we have one outcrop here, then another outcrop here. A lot of people shooting here, we want to check it out, but we just can't because we want to continue existing. And
Within outcrop on the right side, it's arrow shaped, right? So there's like 3 lines. What's in between? Why are there no difference?
there are no rocks, right? There are no rocks, but that's such a good question because that is essentially like if we compare this with like a random distribution, right? We would see that they choose rocks. Now, the reason why they choose rocks is it is like there's no like empirical research as to why this happens, but I can tell you that it's basically because if you live in a rock, you have so many different thermal microhabitats available, right? Like if it's early in the morning, I'm gonna go to the eastern facing side, get warm. Oh, I overheat, I'm going to the shade, coming back again. Then I also have like some sort of space to like protect myself, etc. A really cool thing that we see though is that is right for the Western fence lizard, but that is not right for the color lizard. So the color lizard, instead of like relying on the microhabitat on the outcrop, they just run, right? And they just like they find smaller rocks, they just go under, and they occupy like much larger spaces. Yeah. Danny.
Is that what you're just saying related to differences in how they hunt? I mean, do the fence lizards kind of do more sit and wait? The collar lizards.
Absolutely. That could be another explanation. It's not only a matter, that's what I'm saying, no, like it's such a complex interaction because it's only a temperature, but like if you think about it, okay, like if I'm a sit and wait predator, I'm gonna be on the spot where I know that I don't have to run very far to get my prey. Where is that spot? I eat insects. The insects are also behaviorally thermoregulating and finding the shade, right? So I'm just going to be in the shade because not only I get to thermoregulate better, but I'm also all my prey is over there. Actually, like in hot summer days with this like Mormon cricket waves that we have, we see like hundreds of Mormon crickets in like underneath trees on the side, and they just like lizards just like hanging out there, just like snacking all the time, right? So it is very interesting, no? Like, but there's another like thing of like you might have a pattern that you think is about behavioral thermoregulation, but it is confounded with the pattern of I want to be where there's food, right?
Okay. I'm just thinking about the size of your average Western fence lizard versus the size of a Mormon cricket.
You know, that is a question that I ask myself, but like this is a reference, right? So like this is the Mormon cricket and this is the lizard, right? This is kind of like an average size individual more or less. In a pretty big Mormon cricket, they go to town on them. They hammer them. They like, even if they have to be swallowing for like a couple of minutes, they'll get it out. Yeah. Yeah, this one was one of the most epic catches of all time. Somebody who got a lizard and a Mormon cricket in one go. That was absolutely spectacular. That was Carla, I think, former postdoc in our lab.
Yeah, I was trying to figure out what that, so like, was the lizard in the process of eating it?
So it was weird, like it was in the process of eating it, then it saw us, then the Mormon cricket sort of tried to escape, got on top of its head, and then it all happened like really quickly, and then we just pulled the lizard, and you're like, what the hell happened here? But yeah.
So habitat quality and what makes, so obviously these animals aren't just picking it for resources on the site, but also for the ability to thermoregulate. And so in this system is even like, is there preferred habitat depending on when certain behaviors occur throughout a day? Do they prefer something on one aspect of the slope to another? And do you see, do you have comments on what territory competition looks like and what makes a better territory at this point?
Absolutely, yeah. So I think that what makes a better territory is the fact that I have any temperature that I want at any point in the day, right?
Complexity of the rock.
Complex thermal heterogeneity is called. And like there's like an index to measure it. And like we usually see that individuals that are like, of course we don't have reproductive success data yet, but like we tend to see individuals that live like sort of more territorial males, like Scooby, and be in environments that are more sort of thermally heterogeneous. Like, for example, just to show you guys, like this rock where Scooby lives, is perfect, right? Like the whole thing is on an eastern facing slope, right? And then on the morning I can be here, and then on the afternoon, it so happens that this rock has a perfect incline to the point of like I get a lot of shade, whereas anywhere else in the terrain gets shade.
So you don't see like preference for aspect at all, it's the complexity of the structure.
It's a complexity of the structure. There's like a general pattern in terms of aspect, like at the high elevation side, everything is on an eastern facing slope, and there's almost nothing on a western facing slope. Actually, the only thing that we see, it warms up faster, but like it's a matter of like the return of investment, no? Like, for example, here, let me show this one. So this is kind of like the distribution of temperatures throughout the day, right? If you are an eastern in an eastern slope, you're cool all night long, up until when the sun rises, right? Now, if you're facing on an eastern side, you're gonna get hit by the sun like early, which means that the difference between the temperature that you experience at night and the temperature that you experience in the morning is much higher, right? So if you live on a western slope, you have to wait all the way until later in the day when the sun hits it to be warm, right? So although on average it's going to be warmer, you want to be in the cool side because of the changes in temperature throughout the day. Danny.
Do you have enough data with the juveniles for location data that you could glean information if it would even be worthwhile information to have about how their activities in finding ideal sites, like when are they moving? I'm imagining these individuals have to move through some pretty less ideal habitat to find an ideal place that they can maybe hold territory. So when are they choosing to make those kind of movements?
Good question.
Maybe not just juveniles, what about like males competing?
Good questions. So
even the good males, I mean, I imagine like Scooby-Doo doesn't hang out on that exact rock all the time.
no, Scooby-Doo hangs out on the exact spot every single time.
Like an area that spans a few meters. I mean, you just wonder, like, if they have to make moves, when do they do it?
So okay, so going on stages, no? 99% of the juveniles we find on a tree, like, and it is incredibly difficult to catch it. You can, like Jen, who's been to the field with me in juvenile season, can tell it is disgusting how difficult it is. Like you just have to be under the tree trying to catch it in between. Like I have a specialized pole that is like this length, such that I can like just catch it like this. And we believe that like it's because their thermal sensitivities are like their preferred temperature is a bit cooler when they are younger, and it's hotter when they are older. And we see that pattern like all across the board, right? But then like moving across the terrain, if you are an adult, right? It is kind of like this negotiation of like, what is the cost benefit, right? So I'm gonna move, like I'm gonna only move to like a rock where I can thermoregulate, but I have to like go through like a matrix of very bad terrain. And then if I get to that other side, is it like worth it for me to like move to a rock where I can behaviorally thermoregulate as slightly better or not? So there's this ton of like behavioral decisions. And one of the other things that we're looking into is like, what is, it's also like to some extent the cognition of the individual, no? Like, okay, how good is it at making decisions on from what rocks should I hop to in order to be at the best possible temperature, right? Now, the other problem is like, what is the thing that you're trying to maximize, like optimize with this? We have this metric called the preferred temperature, and we bring them to the lab. We put them on a temperature grading. We put like a heat lamp over here, and then we let them run for like an hour, right? And all the while they have a thermocouple probe connected at their butt, so we can measure the temperature at the whole time, and then we get like, okay, on average it wants to be here, right? So we use that metric, and we are like, okay, it wants to optimize to be at this temperature the whole time. But what if this temperature changes over the season, right? And how is this temperature variable across different individuals? Again, it's really complex, right? And it's one of the things that we're trying to do is embrace the complexity. No.
Predator population size by lizards you may not be able to follow up with it.
Yes, yes. So that is the absolute beauty of this system. That like by doing this mark and recapture, right? By doing this, by having this, I can tell you what is the probability for an individual to survive up until a given age, right? What happens to one individual that we happen to see all the time and then all of a sudden we don't? We don't know exactly. It is possible that other lizards eat it. There's birds that might predate on it. One cool thing that you can do in this kind of experiment is to build a clay model, right? You build a clay model of the lizard, leave it out there, and then wait a couple of days and see if birds pecked on it. And then you use that data to estimate the predation probability, right? It's cool. That's something that we haven't done yet and we want to do. Just got to get like a clay model building party together and we can. Yeah. Ben.
One more.
Yeah.
Okay, so pace of life. So
Yeah.
thinking about pace of life in my bias towards endotherm space, I'm thinking about suites of correlated, repeatable things that are, repeatable within individuals across very complex, different environments. So you're talking about maybe some of these behaviors that are sometimes controlled by their thermal physiology, where they can't perform a behavior just because of the physical limitation at a given time.
Yeah.
So so for and you even mentioned, you alluded to the fact that there's different temperature optimums or preferred optimums per individual.
Yeah.
What does that look like? How much variation is in that preferred? And so when you're going out to say, are you using that preferred temperature when you're looking at these models to look for bold versus shy, or what are you using?
So I gotta preface this with this is not my area, like this is not my project, and like I mean, I'm just presenting here the stuff that like people that I work with have done, just so like we can put this into like a bigger frame. We use the thermal preference, right? But we are only trying, like for now, we haven't correlated the thermal preference that we measure in the lab with the sort of the habitat choice. We could do like a field assay, but essentially a field assay would be like just collecting different body temperatures and sort of making a model for the individual, accounting for time of day, right? So we do have this kind of data. We still need to like dig a little bit into this. Again, I'm just worried about pregnant females for now. And but yeah, when we model that, like we have all of that kind of data, we do see like noticeable differences between like across different individuals and in their thermal physiology. And like that is loosely correlated with their boldness and stuff like that, and loosely correlated with their habitat quality, right? Like another idea is that like, okay, like if you live in a pretty bad habitat, right? Like why not just have like, you might be selected to have like a very warm thermal physiology such that you don't incur in the risk of overheating, right? Like if you don't have any behavioral thermoregulation opportunities, then you'll have to like conform yourself and like be more of a generalist, right? So it's complicated. Again, this is not my main area of research, and there's a lot of unanswered questions.
Thank you.
Yeah. Shall we close on that?
Yeah. No questions from online?
All right. Thank you, guys. Lizards are also cool, not only about birds.